All right, let's do a quick little warm-up with some antiderivatives. So antiderivatives, or integrals, whatever you want to call them, they behave linearly, so I can sort of distribute the symbol over the sum, and I get this new expression here, where I have the antiderivative of each individual function, so e to the x, sine x, and 2. And the antiderivative of e to the x is just itself, e to the x, and there's a 3 out front. And I could say plus c1, and then I have, I don't want that, the antiderivative of sine, which is negative cosine, and I could say plus c2, where these c's are constants. And then the antiderivative of 2 is 2x, and I could say plus c3. But notice, with all these different constants, if I just add them all up, then I could, at the very end, just say plus c. And that'll just be the sum of all those constants. So what I really get is 3e to the x minus cosine x plus 2x plus c. So here's my final answer. Okay, and the reason for this warm-up, the way it is, we're reminding you of a lot of the different types of functions you're going to see. So we have exponentials, trigs, and polynomials. And in this next one, we have a logarithm that's going to appear. So the antiderivative of 1 over x is the natural log of the absolute value of x. And then the antiderivative of 1 over 1 plus x squared dx. So now we actually have an inverse trig function. This is arc tangent of x, and then I have a plus c. Here's my final answer. And then finally, I do another polynomial power rule. So if I add 1 to the power and then divide, I'm going to get x squared plus c. Here's my final answer. All right, so when we last left on break, the last thing we had done was essentially this, sometimes with limits using the fundamental theorem of calculus, but you find an antiderivative, which means finding a big F such that its derivative is some other known function, and that known function is on the inside. Okay, we're going to do a bunch of that exact same stuff today, but it has a new name. So the new name for what we're looking at is differential equations. And a differential equation is just something that has an equal sign, and that's where the equation part of the name comes from. And where the differential part comes from is it also has a derivative. Has a derivative. Okay. So, for example, I have a derivative, I have an equal sign. This is a differential equation. And this might be a very silly sounding definition, and that's totally fine. But for now, let's just classify them. Here's a derivative, here's an equal sign, differential equation. Whereas this one, no derivative is taking place, not a differential equation. Here we have derivative equal sign, derivative equal sign. It's okay to have second derivatives. You can have more than one yeah, as long as you have a derivative. Here's another second derivative. So these are all differential equations. The only one that's not is D. Okay, the thing that tends to happen with differential equations is the independent and dependent variable can kind of be implicit or suppressed or stuff like that. So if we look at part B, which, okay, so I guess we'll just pick it up here. Okay, what this is saying is y is a function of x, and the derivative of y is 3x plus 2. So the independent variable, I'll just do this because I have colors, independent variable is x, and the dependent variable is y. And I don't care so much about that distinction. What I care about is the fact that at the level of the differential equation, so what's written in this box here, there's no x written on the left-hand side, but implicitly this is saying, hey, here's a function. It's the derivative of y. It's a function of x, and it equals 3x plus 2. Right. But, okay, so let's answer the question. The independent variable in this case is x. The dependent is y. We already did that for b, which was the same. And for c, the independent variable is r. It's the thing on top. The dependent variable is p. And what that means, okay, is that this right-hand side is actually way more complicated than it looks in some sense, because this is saying r prime, the derivative of r, which, by the way, is a function of p, is equal to 3 times r, which is still a function of p, plus 2p squared. So when I say it's harder, it's because there's an entire function right here, but the way it's written right here, you might not notice because it just has a letter, right? Okay. So, why do we care about these? Well, just like before, how we had to find a function and all we knew was its derivative, that's exactly what we're going to do again. So, I don't know, let's just look at 4. Is p of r a solution to the differential equation p prime is equal to blah? Right? What it means to be a solution is if you plug it in, it works. Technically, it's if you plug it in, you get an identity, which is a true mathematical statement. But I'm just going to say if you plug it in, it works. So let's plug it in. So I have a p, and to plug p into this differential equation means I do what the equation says. So on the left, I have to take a derivative. So let's take the derivative of p. So, all right, I need to write p in a way that helps my brain a bit before I take a derivative. Okay. So I wrote it so that way the square root is just a power to remind me to use the power rule. And hopefully we see that we need to use a chain rule here. So here we go. So p prime of r is equal to, so this 2 just comes along for the ride. Now I take the derivative of my outside function. So the 1/2 comes down, and I leave the inside the same, and I subtract 1, so now I have negative 1/2. Okay, I leave the inside the same, r squared plus 3r. And then I multiply it by the derivative of the inside, because this is the chain rule. So I have 2r plus 3. And this plus 30 is gone. I could have plus 0, but it's gone. All right, there's my derivative for p. And let's see if this is in fact equal to the right-hand side. So let's see, this 2 and 1/2 cancel. And if I change this exponent back to being a radical, then it looks like 1 over the square root of r squared plus 3r. And this 2r plus 3 is on top. And yes, this is in fact a true statement. This differential equation is true, it's valid for this function, and that means that p is a solution to this differential equation here. When you plug it in, it works. When I plugged it in, its derivative is the thing it's supposed to be. So it's exactly the same as antiderivatives up here. We just need to make sure, oh, where are we? So, for example, the derivative of natural log x is this 1 over x. Like, we've been doing this same process all along. So let's do something a little bit more useful. It begins the same, though. We have y prime is 1 over x. And what this means is, so we should think that y is like the antiderivative of 1 over x. And there's a reason that I just say is like. This is not an equal sign. I'm just saying it's like this thing over here. Now, this is an equal sign because I can connect, all right, what is the antiderivative of 1 over x? It's the natural log of the absolute value of x plus a constant. So my y function, I'll be able to pin down what it is if I can just figure out this constant. So for now, I'm going to write y of x is equal to natural log of x plus a constant where, okay, and this here, this extra bit of information, it's called an initial condition. Okay. And that's how we're going to figure out C. So where that happens. So let's plug it in. So y of e is the natural log of e plus c. But on the other hand, that has to equal 0 because we're told it equals 0. So natural log of e, that's 1. So this says 1 plus c equals 0, which says c is equal to -1. So now I can conclude, okay, y of x is the natural log of the absolute value of x minus 1. Here is my solution. And we could check, if I take the derivative, I satisfy the differential equation. It's true that the derivative of this is 1 over x. But then also if I plug in e, I satisfy the initial condition. So this is called an initial value problem. And it's solved in 2 steps. We first find the antiderivative, then we plug in the initial value to figure out c.